Hi, I'm STÖK, and today I'm gonna learn something new. And for this reason I brought on Christoffer Jerkeby, also known as KUGG, to help me understand the beginner's guide to fuzzing, or maybe not just a beginner's guide, but it's going to be an introduction to using AFL. Hi Christoffer.
Hi, I'm KUGG.
Hi KUGG. KUGG and STÖK show, yay! So you and I, outside of this camera situation, has been playing around a little bit with fuzzing, and I kind of convinced you to get on here and teach me and others how this actually works and talk a little bit about fuzzing. So without any further ado, please take it away.
All right, so today we're gonna play with AFL. AFL is a fuzz testing tool, and it's a method to find bugs in binary programs.
Fuzzing is sending a lot of requests into something, right? Is that the idea?
Yeah, so you have an original input in a dictionary of possible inputs, and then it's taking that original thing and transforming it every time it runs a new iteration, and it runs thousands of iterations every second.
So this is automation?
Yeah, definitely. You have to automate it, otherwise it won't work.
Okay, show us how you do it.
Okay, so essentially when you want to do this, when you want to run AFL, you have to use a compiler. So compiling software, you do it with, in Linux you do it with GCC normally. And GCC is, by the compiler program called make or makefiles, is defining an environment variable called CC. So CC equals GCC is an environment variable that's automatically assumed every time you do a compilation. And compiling programs means to take all that C code and turn it into a binary program.
Cool.
With AFL, you're going to replace GCC with your thing. So our thing is AFL-GCC, and setting that environment variable, we can now compile the program with something called instrumentation built in, and that means that it's changing the code that you're building so that every time it comes, the program turns into a certain state, then that's registered by something called the instrumentation instrumenter, or the instrumentation state.
Ah, cool.
Right, so having instrumentation means that you can know what's going on inside of the program when you run it. And this is a really nice feature with AFL that other fuzzers aren't that good at. And that means that AFL can understand when you have reached into a point that you're interested in reaching. Say you want to break a certain point in a certain place, then AFL will know if you are there.
So it's some kind of breakpoints. So it's just measuring all the time, like where are you in the code, and if something breaks, it's gonna know instantly.
Yeah, it's definitely like a breakpoint. I think this is more what you could call a function hook, where you take a regular function, you put yourself in place of it, and that's something that it can put into some kind of a live documentation that it's understanding and learning from that. So it's a sort of a self-learning program.
Cool.
So once you have compiled your program, you can start it using the AFL fuzzer. That looks a bit like this. AFL fuzz is the name of the program you want to run. AFL, by the way, is a program that you can download using apt-get install AFL. That's it. So it's
super easy setup.
Yeah.
Just get started, and then you're up and running.
On different CPUs, you have some different tuning options that you want to set. And those tuning options is something that AFL will tell you what to do with. So you can adapt to multiple cores and you can do different things, but it depends on your architecture. We've already done this, but AFL will tell you exactly what you need to do for your CPU.
Cool.
So the -i argument, it gives you the input to the program. And we're going to take a look at the input to this program because we are today fuzzing a HTTP server.
Oh yeah, cool.
And the HTTP server we are fuzzing, we did one more take with this last week, and we were ready to publish it when we realized that we had found a 0 day and we had to report it, and that meant that we couldn't really publish it at that time, right?
So this is the second recording for that obvious reason.
Yeah.
When you're finding 0 days during your fuzzing sessions, it's a good thing to report those.
Yeah. So we're gonna show you how we found that 0 day, but we're not gonna show you what program it's in, but it's a HTTP server, we'll give you that much. So if you look into the input directory, I have a default configuration file that sort of looks a bit, this is a fake configuration file that I wrote. It's similar to the default file where the domain name is fsecure.com, which is my employer. The configuration file is pretty straightforward. We are today going to fuzz the configuration file parser. And the reason why we want to fuzz this parser is because we are assuming that an attacker has arbitrary write access, but wants to escalate their privileges to root or get access to whatever that server is doing. And since you have write access, if you write to that configuration file something arbitrary and bad, then maybe you can make the process crash. And if the process crashes, then you can overwrite its memory. And that's what we're going to try to do.
Or just wait for it. Let's say that we had a malicious conf file that we created, and what we would just do is to either just crash the daemon itself, right, or just wait for it to reboot, and then hopefully, you know, nobody's noticing what's going on, and voila, suddenly we have root access. Yeah,
exactly. And in this case, the input to AFL is that configuration file. So the default configuration file is pretty much what we need as an input. As an output in this case is a directory where AFL is syncing whatever it's doing with other processes. So if you run this with multiple cores, you can synchronize that output using the output directory. And this is something that you can synchronize between multiple machines even.
So if you're having a cluster running it and you want all these machines to know what's going on, that's a good thing to just map. Can you map this over network, or is that not recommended?
Yeah, you can. So what the master process does is it synchronizes multiple slaves using the output directory, and then it gives the slaves a queue of things to do. So if there is a certain lag between the machines, that queue will sort of work itself out. So as long as the lag is not longer than the queue, then the slaves will have something to do until the master realizes that this is where we want to go with the fuzzing. So the output directory is pretty important. It also contains wherever our crashes and things that we found out during this attempt is going to end up in the output directory.
Oh, cool. I got a question though. I know last time we talked a little bit about it. And it didn't really straighten itself out for me. But you mentioned that it would be a good idea to not run this on SSD drives.
Right. So the output directory is a directory that is written to a lot of times. So it's written to for every single instance. In my case, it's writing 2,000 times every second. And that means a lot of writes. And for an SSD, that can be a bit harmful. SSDs are not always ready to handle that much data, and it can wear them out quickly. And therefore, there is something called TMPFS, which is like what you have in /TMP on your machine, where you can write as many times as you like because it's on RAM. And it's also very quick. So we have the input, which is the config file. Actually, we can have a directory full of inputs. So if we had a bunch of other config files there, that would be fine. And that gives AFL inspiration to how to destroy things.
Oh,
okay.
So it's fetching all this other stuff as well, and he just thinks about, maybe if I try this.
You can put random data in there, and you can put legitimate data in there. Eventually, AFL will figure out what type of data this program wants, or doesn't want. So the next argument for AFL is to type in HTTPD, and that's the name of the server that we are fuzzing. And -c is the argument for a config file, and then we type in @. @ is the variable where AFL will input the fuzzing mechanism. So this is where it will go and attack. So if we run this, it's going to initiate by trying to find basic paths into the program and just try to understand the program. And now it's started. And even like in the first second here, we found a crash. And when this turns red and it says one unique crash, then we have, essentially we have the beginning of a 0D. Because this is, yeah. And that's
So
all the time
now.
it takes.
We got two
sometimes.
now.
Here's the second one coming up. And so now we're running in 2000 attempts a second. You can, I mean, you can scale this as much as you want to. If you have more cores, you can scale this much faster. And if you do that, then you can find more bugs basically. And if you are pressed with time, let's say that you're a developer and you want to test your own software, then maybe you want to do this in the cloud where you run it on multiple cores and you get it up to maybe 30,000 tries a second, because that's going to take the attack space or make it much shorter.
Absolutely, it's like if you can run this like not just one time faster, like 10 or 20 times faster, of course you're going to save like a lot of time with it. Yeah. Isn't it going to be like very CPU intensive and very expensive though? If you're, let's say you're putting it in a cloud storage somewhere.
Yeah, I mean it uses only CPU. So if you have a solution where CPU is cheap and the rest is expensive, then that's fine. But it's using a lot of CPU and somewhat a bit of a network if you have it networked. But it's only using as much RAM as you allow it to use. So you can make it crash and hang in different ways.
God damn it! That means that I'm gonna have to buy back all my old rack servers now again.
Yeah, I mean, so CPU costs nothing if you own the server. If you have your own servers, then this is what they're for, right? Use GPUs for cracking and CPUs for fuzzing.
Yep. Oh man. Oh man.
So right now we're running on 12% of the CPU. That means in this case that we're running on one core only, which is enough for our example. And in another cast we can show maybe how to increase that number, because if you use more than or up to 100% of the CPU, that means all cores, then you can make a lot of damage. And that's what we want to do, right?
Hey, let's do that. That would be exciting. And is this ever going to stop though? Or does it ever feel like I'm done?
No, this never exhausts, because it actually has ways of muting the output and coming up with new ideas until forever. So I think this can pretty much go on forever in this case. But you can exhaust the search space for a given input. So imagine you know that a program only takes true or false as an argument, then that search space will be exhausted pretty quickly and the program will just run on hot fumes basically.
Cool. So we currently have 2 crashes. What does that really mean? Like, what do one simply do with the crashes?
Yeah, so now I interrupted the program typing Control-C and it says, we're done, have a nice day, thanks, and I'm done too, right? So now we have the output directory. Let's take a look at that. So in the output directory, you can see the crashes directory, the fuzz bitmap that gives an information about where in RAM are we at this point. Statistics, hangs, that's an option to crashes. So a hang is when a program doesn't finish in a given certain time. So you put a timeout on a program, you can assume that it's not supposed to hang until this or that, or it's supposed to finish before that particular time. And every input that exceeds that ends up in hang. Plot data, don't know. The queue is where the next input is queued. Let's look at the queue just for now, because this is pretty interesting. So looking at what it's doing, it shows the original file in the queue where it started, and then it shows where it's at. So right now, this queue data here is on position 25 and it's flipping 1 bit. And we can look at what that looks like. pretty much looks like a shorter version of the previous file. It's flipping something based on what it did previously. And every time it does this, it learns that parsing the config file at this point gave that output, and parsing the config file at another point gave something else in terms of where in the map it's ending up. Let's move into the crashes directory, because that's what you wanted to see, right? Oopsie.
Yep.
So there is a Readme file, and this Readme file is pretty good. The Readme file shows what you actually ran to find this bug. And that's something that you can give to a organization that does this testing, so that they can actually know what's going on. I mean, if they want to reproduce this bug, then it's good to have that command line saved. So this entire directory is relevant for anyone who wants to reproduce it.
Cool.
Inside of here, we have the config file that caused the crash. So this is a config file that has a character called 8A in it, and that's like a non-ASCII character. Maybe that's the reason why it crashed. Maybe there is another reason. It says that the log access file is called hard bracket. That looks kind of weird as well. The doc index has a bracket as well. Maybe that's not it. We don't know exactly, but we can find out eventually. We can look at the other file for now. So this is two files representing two different crashes. All right, so this is a weird one. And weird is good.
The weirder the better.
Yeah, so now it's actually managed to produce this kind of a string here where it says TMM verlis, whatever that means.
Yeah.
And that's just the machine talking. And in other cases, when I did fuzzing with pictures before, I started with basically an empty file, and it actually managed to produce, in a few days, it managed to produce a valid JPEG header by just looking at the reaction from the programs. Like, if I want to get a step further, I have to type in this position.
Ah, cool.
So here it's
actually created an image for you.
Yeah, and that's
slowly just built it up.
Yeah, that's the definition of mutation, right?
Cool.
So this is a configuration file that also causes a crash, and there's also non-ASCII characters in a comment on the last line. Maybe that has something to do with it. I'm not exactly sure yet. So I'm gonna back out to this directory where the HTTP server was.
Yeah.
And now I'm gonna run GDB, and GDB stands for GNU Debugger. It's if you are into CTF or any type of security research, GDB is a good tool to know. It's older than me, and it has a lot of good plugins for it that can enable you to write exploits later.
Cool.
So we are going to run GDB on HTTPD, which is the name of the server. And right now I didn't compile it with debug symbols, so it's not super easy to find out what's going on. But if I have debug symbols on, it's going to tell me on what line in the code the bug exists, which is pretty nice.
Sweet.
I'm gonna set up an argument which is -c. This is the configuration I do for the program. So I type set args -c, and then output crashes, and then I paste in the name of that file, the second file that caused a problem for us, or that caused a crash. So this is now the configuration file of the program. At this point, I can set up a breakpoint myself if I happen to know what I'm going for, if there's something in particular I'm interested in, but right now I don't know. So now I can type run or R. Some people put the breakpoint on main, for instance, which is usually a function that starts initially in the program. In this case, I know there is no main function, so it's not gonna, or the main function doesn't work necessarily the way I want it to. But you can put the breakpoint on either an offset into the file or into a function that you think caused a crash. This is much easier to do if you have debug symbols on. So if I type on run right now, then you'll see that there is a segmentation fault. And this is not supposed to happen normally. Like, a program is not supposed to seg fault every time it reads a config file. Then you have a serious vulnerability. In this case, this is a vulnerability where we are running as an unprivileged user writing to a config file, right? And the service is reading that config file, and it's corrupting memory, causing a seg fault somehow.
Yes.
And it's doing it as root, because root is needed to start this service and bind port 80. And this is running as root initially, and then when it's running, it's crashing, and I'm in control of the memory. So that's a privilege escalation of a kind.
Sweet.
And here we can do a backtrace. A backtrace where it shows the state of the program, and you can look into the info about the registers that you're dealing with right now. And
this is like, I have no idea what's going on here.
I'm sorry about that. There are
this?
more tutorials that can go into depth and show how to do this, the exploitation and proof of concept state, because what we have right now is a crash, right? We have a denial of service vulnerability. That's local, by the way, but it's still something. After this point in time, we start figuring out, why is the return pointer here at this point? Why is it there? What happened? How did this occur? If we do that using GDB, we can start figuring out and writing a proof of concept exploit. Have you done OSCP, by the way?
The buffer overflow part is very much like this.
Right. So this is
XP,
exactly that you have to do at this point. You can input a certain pattern into the program and see if that pattern reoccurs. And if you do that, you can see where it is in memory and what you were able to overwrite using the original config file that we looked at. And this is pretty much how you use AFL.
That's amazing. So the whole idea with AFL is for us to, by automation and a little bit of, I wouldn't call it AI, but at least a little bit of learning, that it learns what's going on in the process. And then when it crashes, it's trying to replicate it and see what happens again and again and again and again until, whatever kind of break that this happens. And it outputs that file, and that's where the exploitation creation begins, right?
Yeah.
This is where when people write exploits, this is what they do.
Yeah, and this is how you find the bug, and this is something that I already in this point reported to the vendors. I told the HTTP server vendor what the bug was about, how it was found, what the stack looked like by using GDB, and gave the core dump file to them so they could reproduce that bug in their local environment and see that this is a problem.
That's very responsible of you. I'm very proud.
In bug bounty, do you think this is useful for you?
Maybe it's not this situation, because in bug bounties, if you get this far, you report it and get out, right? You can touch just a part of a disk, that's game over. You've done your work. You don't privilege escalate further on. You might just be doing it in pen testing, but in bounties you don't do it. But I see other areas where this can be very interesting. Like there's file formats, there's different other servers, parsers, and things that are being used by our industry, that if you can find an exploit or something that breaks that could turn into, I don't know, a DOS or some kind of other misconfiguration happening. Maybe, I don't know, maybe even a little bit of memory leak if you're lucky.
Right, so I mean, if you have an input like a zip file or a JavaScript parser or something where you can upload maybe a HTML document that's getting parsed, or CSS getting parsed, or maybe a video file or something. There's
all these parsers out there that's gonna have to deal with shit. And I know you and I have been doing some research on this, and eventually I would recommend anyone to at least start to doing a little bit of fuzzing. I think it's super fun and so rewarding when you see that crashes sign coming up. You're like, ooh.
Yeah, so I mean, it's so easy to get started with, and the types of bugs you find, you can use them on a large scale for much longer time, because these low level programs are reused identically on multiple platforms. I mean, so imagine that we were playing with a media transformation format and found a bug the other week, and that's something you can reproduce forever, like it's reported and all, and they don't seem to want to fix it because it's just a hang and not a crash. And it's like, okay, fine. So then you can use that to identify this media transformer tool.
Well, all this is super interesting, but KUGG, you've been doing this for a while, and I know you got some aces up your sleeve. Can you tell us a little bit more about that?
So we're setting up a webcast where you can follow along and live answer and ask questions. How to get started with fuzzing, and if you have got stuck recently with it, you can get help there in the webcast, and it's on F-Secure Labs, where me and my colleagues publish lots of talks of things we're doing, basically.
Oh, that's amazing. So it's going to be a community-based thingy that F-Secure is doing to get more people into fuzzing.
Yeah, so this is the F-Secure Labs channel on YouTube, and it's available to anyone who wants to watch it.
That's amazing. God damn it, I learned something new today as well. And I'm going to be a huge fan of the channel, of course. I'm going to glue myself to that. So thank you very much for taking your time and learning me or teaching me about AFL.
Thanks for joining in, guys. It's really fun to teach, and thank you, STÖK, for having me. Appreciate it, man.
Awesome. Have a
Bye.
good one. Bye.